what is the memory access time? Memory access time. It is a time interval between the microprocessor makes a request to a memory and till the data becomes available. So now let's assume if we are using a microprocessor, okay, and then it is in phase with memory. So for this interfacing, so we have some address lines. Let's assume we have A address lines and W data lines. So the memory is 2 to the power n cross W. 2 to the power n cross W. It's A address lines. It is 2A cross W. So it means the memory is capable to store 2 to the power A locations. Each of how many bits? W bits. In addition, microprocessor will also provide some signal that is called as chip select, or we call it as address probe. We call it as address probe. It is connected to the chip select. Okay. Then we also have a read-write bar signal. So what does address probe means? Address probe means that now address probe means that microprocessor. If address probe is 1, it means that microprocessor has generated a valid address. It's not always necessary. It's not always necessary that microprocessor always need the data from the memory. Sometimes it needs data and sometimes it does not need the data. Now let's assume if we divide an instruction into 5 cycles, any instruction. So there are some phases of instruction execution. Let's assume this is an instruction add R3, R2 and R1. What this instruction is doing? It is adding the contents of R1 and R2 and store it in R3. But if you divide this instruction into 5 cycles, so there are different cycles. Instruction fetch stage, instruction decode stage, then operand fetch stage, then execute stage, and then operand store phase. Now this is typical the cycles of instruction execution. So now what microprocessor is doing in instruction fetch stage? In instruction fetch, it is fetching the instruction from memory. So it means if it is fetching during this phase, so microprocessor will be reading data from memory. So in this case, microprocessor is, when microprocessor intends to read the data from memory, so it means it is sending a request to memory. So in this case, address probe should be 1. Address probe should be 1. And there is a special register in a microprocessor. It is called as program counter. What's the program counter? If you remember your program counter is a register that points an instruction in memory. So now let's say, and if you remember the instruction set encoding that we did in the last class, if you remember, so this was an instruction. Let's assume this was an instruction. Opcode field. What was the other field?
Operand.
RD. RS1. RS. There are 3 fields. So actually this is an instruction which is stored in memory at any arbitrary address. Let's assume this address is, let's assume this is the memory, and this instruction is stored at an address 0x5324. This is, so in this case, program counter is pointing, program counter of the microprocessor is pointing to this address, and this contents is loaded from the memory to the microprocessor. So there is a special register within the microprocessor which is called as MAR. MAR means memory address register. So memory address register is a register within the microprocessor which is pointing to any location in memory. So let's assume if this MAR has an address, what's this address? Let's assume this instruction is stored in opcode RS, RD, RS1 and RS2. So it is pointing to this location. So this MAR for this particular example is storing an address 0x532. So this address will be available on the address bus. So instruction fetch is a read operation or write operation? It's the read operation. So read operation, so what will be read write bar? 1, because microprocessor wants to read the data. Okay, so it means when it wants to read the data and it will provide, so what will be the direction of data?
From the memory
to the microprocessor. So in this case, so my MAR, this address is put on the memory, this particular location will be accessed, and this, the output of the instruction will be put available on the data bus. In the previous example, in the very simple example, we said that let's assume that the output for add is 0. Output for add is 0. What is RD here? 3. 3, then 2 and 1. So this data will be available on the data bus 0, 3, 2, 1. And it will be stored in the one of the register into the microprocessor. It is called as memory buffer register. So memory buffer register contains the data that needs to be transferred to or from the memory. Okay. So naturally, in this case, this data instruction coding is then used in the memory buffer register. So the memory buffer register, let's assume this value is read for this particular simple example. So now address probe is 1. Read write bar is 1, it's a read operation. Okay, now when this instruction is loaded from the memory to a memory buffer register, so now the instruction fetch stage is complete. Now we need to decode the instruction. So next phase in the instruction decode phase. So instruction decode phase, there is a decoder within the microprocessor that decides that what to do. Okay, it decides whether it is an add instruction, subtract instruction, multiply or divide instruction. So there is a special register within the microprocessor which is called as instruction register IR. So this contents of the memory buffer register is then transferred into 0, 3, 2, 1. Then when this instruction is the contents of the memory buffer register is transferred to the instruction register. So then now this comes the roles of the instruction decode phase. And now instruction decode phase decode this instruction. It decides what type of instruction it is, whether it is an add instruction, subtract instruction, multiply, divide, logical shift left, logical shift right, or any type of it, or branch instruction. Okay, or jump to subroutine instruction. There are a lot of instructions in the assembly, and you already studied these in more detail in your undergraduate course. So now in instruction decode phase, microprocessor is decoding the instruction. Which instruction? Where the instruction is lying within the microprocessor when it is decoding? Instruction register. How does it identify that it is an add instruction?
0.
Output. For the output field of the instruction, not 0. From the output field. Now we are talking general. The output will be different. Now in this particular example, we assumed that the output for the add is 0. If we assume that output for the add for this particular example, if we say that the output field, so output for the add, 0 for add, and let's assume 1 for subtract and 2 for some other instruction. So from there, so actually, now in instruction decode phase, does microprocessor need some data from the memory during this phase?
Instruction?
No. Because now the data is now available within an internal register of a microprocessor. Now in this case, what should be address probe now? 0. Address probe should be 0. Okay, now in that case, address probe is 0, read write bar is 1, and now we also need to provide the address of the location. So in this case, what is the address that we are providing? 0x 5324. 5324. This is now, let's assume that if this address is in hexadecimal, this is the hexadecimal representation. So now in instruction decode phase, now address probe is 0. So what does this address probe mean? The address probe is 1 when microprocessor will generate a valid address. And microprocessor will generate a valid address. Microprocessor will generate a valid address when it intends to read the data from memory or write data to
memory.
So in this scenario, so in this case, address probe will be 0. Okay, now in the operand fetch stage. Now if we compute and if we consider any kind of statement in C, let's assume C is equal to A plus B, and I told you that it is an expression. C is equal to A plus B. Okay, so we have some result operand, and then source 1 and source 2. So whenever we want to perform any computation within a C or a high level language, now we should be interested that where the operand lies. So there are different possibilities that the operand will lie. So the operand A, B or C, it can be any operand. So this C is a result operand, A is source operand, B is your source operand. Okay, the operand may lie within a register. Operand may lie within the register. So this comes here, comes the role of the addressing mode. So which addressing mode is this? Add R3 or 2 or 1?
Register.
This is register addressing mode. In the register addressing mode, the operand lies
in the register.
With the register. So now another addressing mode. We can also have another addressing mode. For instance, let's assume we say add R3, R2. Let's assume if some microprocessors support this instruction, add memory, some address 0x9234. So it means that now it's an add instruction. The result operand is in register R3. The first source operand is in register R2. And the second operand is in the memory. At which address? 9234. Maybe there is some address in memory 0x939234, and maybe the operand is lying here. So which addressing mode we are using here? Absolute addressing mode. Absolute or direct addressing mode. I will teach these addressing modes maybe later on, and then we will study this in more detail. So okay. So now if just done it for at high level. So if we want to perform any computation, so we will be interested at where the operand lies. The operand may lie within the register. The operand may lie
memory location.
Within memory that is pointed out by any address, or the operand can be a part of instruction. When the operand is a part of instruction, which addressing mode is this?
Immediate addressing.
Immediate addressing mode. So now let's assume if we say move, if we say add R3, R2, 5. So it means that now we are adding the contents of R2 to
5.
So it means that the contents of R3, it means the contents of R3 will be updated with contents of R2 plus 5. In this case, the immediate field, in this case, now this is one port, opcode RD, RS1 and RS2. There is also one port. It's, the instruction will look like this: opcode RD, RS1 and 5. Immediate. So we can also call it add I. What does add I means? Add immediate. So add immediate. Maybe the opcode for add I, is 8. When we use add I, what does it means? We are now adding an immediate value to a register. So if we have an add I, let's say we have add I R9, R3 and hash 5. So how the output will look like? What will be the output? 8. What will be RD? 9. What will be RS1? 3. What will be immediate value? 5. So in this case, it will not add the contents of R3 with register R5. In this case, it will add the contents of R3 with an
immediate value 5.
Immediate value of 5. And when an immediate addressing mode is used? When an immediate addressing mode? Okay, if you have a C++ language, so when immediate addressing mode should be used? When it should be used?
Loops होंगे I is equal to I plus plus.
No. When it should be used? Just think of the scenario. When it should be used? Yes. If you want to initialize some constant value, like let's do if we say int c is equal to 5. Now you are initializing a value of 5 to c. So it will maybe the assembly instruction is move r3 hash 5. So it means now you are storing the value of c in which register? R3. So immediate addressing mode is used to initialize constant value, or immediate addressing mode can be used to. Okay, so now if you look at the microprocessor, so what's the job of a microprocessor? What's the job of a microprocessor? Microprocessor can perform only 3 tasks. It's very simple. At a very high level.
Read, write, execute.
No. It performs data transfer. Microprocessor has 3 jobs. One is data transfer. Number 2, data transformation. And number 3, control instructions. What's a data transfer instruction? Transfer data from memory to register, or from register to memory. So this is a data transfer instruction. And what are classical example of data transfer instruction? move. Okay, now data transformation, it performs the transformation on the data. If you look at the state of the microprocessor, so the state of the microprocessor is determined by the state of the registers, the values stored in the register, and also the state of the memory. So the state of the microprocessor is changed by data transformation instruction. So now let's assume that if we have A plus B, so it has some values in anywhere, maybe register or maybe memory. So when you say C is equal to A plus B, so it means that now the contents of C are changed. And the state of the microprocessor is different at different time instant. Maybe at cycle 1, register R3 may have a value of 5. Maybe at another instance, the value may be changed. So the state of the microprocessor is determined by the states of the registers and the state of the memory or the contents of the memory. Okay, and the data transformation instruction or type of instruction that change the state of the microprocessor. And control instructions that change the flow of the program. They change the flow of the program. So typically the instruction data executed sequentially if you want to change the flow of the program. Okay, so what instructions are used to change the flow of the program? Jump,
loops,
branch
equal branch, conditional jump instruction and unconditional jump instruction. You may have studied this in more in your undergraduate course. Okay, so now coming back to our topic, so if you look at the different phases of instruction execution, so instruction fetch stage, address stop is one, means microprocessor has generated a valid address. Instruction decode phase, no. Now in operand fetch stage, now it depends on the addressing modes, where the operand lies. If the operand lies in memory, so it will then fetch the data from memory. And if it want to fetch the data from memory, so what does it need then? It needs an address. It's an address. And if the operand fetch state, so operand fetch state, the address stroke may be in this particular example. For this particular example, the address stroke is 0. But if we have this instruction, that let's assume we have this instruction, like add R3, R2, and like this instruction. For this instruction, the first operand is in register. However, for the second operand is in memory. So you need an address stroke for this. So in this case, this address will be transferred to MAR, and that memory location, and data will be read and go into MBR. What is MBR? Memory buffer. And this, then it will go to ALU. For ALU, you have some first operand, and then second operand, and then it will in ALU it will perform the computation, and after that it will execute the instruction. So let's assume if you look at the internal of the microprocessor, so in internal of the microprocessor there will be some invisible registers. Let's assume for ALU this will be first operand to the first register and the second register. This is internal register, and this is the result register. The result will be computed and then will be stored into either a register or memory, depending upon that where the operand lies. So we have some source operand or destination operand. So let us assume if we have this instruction, add, let's assume add memory, let's assume this address 0x3462 R3 R2. So what we are doing here?
R3 2 को ऐड करके मेमोरी
R3 R2, for this we don't need an address stroke, but for this
we need
address stroke is 1. But for this case, now because the destination has to be for operand store phase, so in this particular example, what will be address stroke? 1. Read operation or write operation?
right.
Okay, so now in principle, so actually whenever memory is interfaced with the microprocessor, so whenever memory is interfaced with the microprocessor, we are always interested in the access time of the memory. We are always interested. The faster we get the data, the faster we can perform the computation. Now there is a complex trade-off. Now if you look at today's scenarios, so actually the data size is growing. When the data size is growing, so you need larger memories. When you need larger memories, so it can accumulate a lot of data. When it can accumulate a lot of data, then it provides an advantage, but there is also a disadvantage. If a structure is larger, its access time will be
more
higher. When access time is higher. So that's the reason that whenever we want to design an even for a particular memory size, we are always interested in reducing the access latency or the access time of the memory. Okay, and we studied different type of memory in the previous class. What kind of memories were there? DRAM, SRAM, rest track memory, spin transfer random access memory, okay, and phase change memory. Okay, if you look at the SRAM and DRAM memory, it stores the data in the form of like voltage. In the form of voltage. And what about the non-volatile memories? In the form of what? Resistance.
Charge.
High resistance and low resistance. If you look at the phase change memory, there are two states. One was amorphous and one was crystalline. One represents the high resistance states, another low resistance. If you look at spin transfer torque memory, it was parallel and anti-parallel. When the polarity was parallel, the resistance was low or high? Low. Which it was anti-parallel, resistance was high. Okay, and in rest track memory, we already studied that we have some a track consists of multiple domains, and we have a read-write access port. And if you want to access the data, so we need to shift the data. So okay, so now we will in this context we will study different type of memory, technologies, and then we can see that what kind of optimizations we can do with these kind of memories in order to reduce the latency, or in order to reduce the power. So we will study these kind of optimization later on. Okay, so now another thing that is also important, like in memory, is also the size of the bus. Size of the bus or the bandwidth that's available to a microprocessor. So now let's assume a scenario that now we have a size of W. let's assume this W is 64 bits. This W is 64 bits. And then if we need 128 bit of data, then what we have to do?
2 cycles make a
So in the first cycle, then we have to access the next data in next cycle. So it also depends upon the bus bandwidth. Okay. If we increase the size of the bus, what's the advantage? Throughput. The throughput is, what's the disadvantage?
Space ज़्यादा होगा.
It increases the number of chip pins. And increasing the number of chip pins is actually the basic constraints of the memory. Okay, so it will increase the number of pins. So there is always a trade-off. Trade-off between these things. So if you look at the memory, like the access time, so access time can be defined as the time interval between microprocessor makes a request. Let's assume microprocessor makes a request and at the time between the data becomes available. So let's assume microprocessor makes a request at this time T0, and when the data becomes available here T1. Okay, so this microprocessor makes a request and then the data becomes available. So what is access time now?
T1 minus T0.
T1 minus T0. Okay, so for some kind of memories, like for instance for SRAM memories, now we will study different characteristics of memory, how they differ in the access characteristics. So we will now study different type of access characteristics of different memories. Now let's assume we have an SRAM memory.
Did memory have a signal for microprocessor to tell the data is available now?
Yes, it also depends upon whether it's a synchronous memory or asynchronous memory. So for synchronous memory, so let's assume if both are synchronized with the clock, okay, and let's assume it's running at 1 gigahertz. at 1 gigahertz. So the time period is now 1 nanosecond. When the time period is now 1 nanosecond, it says, okay, when it accesses the data, so it will get the data in 4 cycles. So in 4 cycles, so it means that now the latency is 4 nanoseconds. Okay, so now this is the example of synchronous memory. But if the memory is asynchronous, okay, sometimes it's also possible that the memory is accessed by multiple devices, and there are multiple requests. When there are multiple requests and bus is limited, only one request can be served at a time. So actually, when it accesses this data, so in that case we need another mechanism that is called as a handshaking mechanism. In the handshaking mechanism, microprocessor tells the memory, okay, I make you a request, and then memory informs the microprocessor now that data is available. This is called as handshaking. So in that case, this access time is fixed for a synchronous memory, for random access memory, for SRAM, but for other type of memory, this access time may vary. This access time may vary. And now for different type of memories, we will study it how it varies. So before understanding this, now for any type of memory, this access time may be fixed, or this access time may be
variable.
And this is also a lot of things. If you look at the process variation, even there are some chips that are with the same fabrication technology, and because of the changes in the process variation, one memory has an access time of 4 nanoseconds, and the same memory of the same size with the same fabrication may have an access time of 5 nanoseconds, because due to the imperfection in process variation. So now this is a very wide topic. I am not going into much detail at this point, but just we can say that what's the definition of an access time? Access time is the time interval between the microprocessor makes a request till the data becomes available. This is just that. So the access time may be fixed or may be variable depending upon the type of memory that we are using. Now first we are studying an SRAM memory. So in SRAM memory, in typically most of the cases, the SRAM memory has some, if you are using an SRAM memory, typically its access time is independent of the location that needs to be accessed. So now let's assume that if it's an SRAM memory, okay, and let's assume its access time is 4 nanoseconds. Access time is 4 nanoseconds, and we are using a microprocessor, and microprocessor is working on 1 gigahertz. So what is the clock? The clock is 1 nanosecond. Clock period. Now let's make it just like 3.8 nanoseconds. Okay. So now what should be the access time? 4 cycles, because you also need some margin. Okay, so it means that so 3.8. So it means that now one cycle. Now this is a microprocessor. So this is 1 nanosecond, 1 nanosecond, 1 nanosecond, and 1 nanosecond. So if you send a request at the active edge of the clock at this point, so 1 nanosecond, 2, 3, and 4, and then the data will be available from here. You also need some margin, okay, and then you get the data. So in this case, in this point, microprocessor make a request, and at this point now the data becomes valid. And in typically most of these SRAM devices, this access time is typically fixed. In SRAM, the access time is constant for any location that we need to access. So now let's assume if we have an SRAM memory and it has the starting address is, let's assume, 0x0000, and then the next address is 0004, and last address is 0xFFFC. So the first location, the second location, and third location, and so forth. So on, these are all locations that are in memory. So if you access this location, or if you access this location, the access time is constant. Why it is same? This is a very good question. Why it is same? Now can you think why it is same? Anybody can give you an answer? Yes.
At a time, the decoder selects.
Yes, the decoder selects. If you look at here, so now let's assume I am giving you an example of very simple decoder. So let's assume we have 8 locations. How many locations? 8 locations. 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So which location will be accessed? 57. Sorry, 0 to 47. So you need which decoder? Because there are 8 locations. You have 3 address lines. So 3 address line 3. So which decoder do you need? 3-8 decoder. So if address is 0, 0, 0, which location will be enabled? First. And 1, 1, 1? Last. And typically the latency of this decoder is same. The same. That's the reason that for NSM. Okay, now if you look at a very big structure, big SRAM structure, there can be multiple decoders. We are not